Hi, I'm Manikanda. I'm a fourth year undergraduate student at IIT Madras. In the following series of videos, I'll be explaining a few control systems lab experiments performed using the LEGO Mindstorms kits. These kits are highly reconfigurable and hence can be used to design various experiments across different domains. They are also not very expensive. Also, they are very portable and user-friendly. Thus, they can be taken by the students to their dormitories. A creative student will be able to design his or her own experiments in order to get a more in-depth understanding of the curriculum. Also, these kits induce curiosity and excitement and thus provide for an enjoyable learning experience. The first experiment that we'll be looking at is controlling a servo motor using the LEGO Intelligent Brick. So what is a motor? That's the first question that we must answer. A motor is a device, as you can see, that converts electrical energy into mechanical energy. A servo motor allows for precise control of the angular position using a rotary sensor for feedback. Now, it is well known that a DC motor is a linear system. A linear system provides a sinusoidal output when excited using a sinusoidal input waveform, with perhaps magnitude scaling or phase shift. So, we need to verify that this motor is a linear system. In order to do that, we will write a Simulink program and run it on the NXT brick. So, let me show you the code in Simulink. As you can see here, we generate a sinusoidal waveform and give it to the motor. And we read this motor response and log it using the scope block. To run it on the device, first we will have to turn on the NXT brick using the orange button. Once it is on, we will have to press the play button in the Simulink program. Now that we have completed the experiment, let us observe the results using a MATLAB plot. As you can see, there is magnitude scaling and there is a phase shift between the two sinusoidal waveforms. This proves that this is a linear system. We can repeat the same experiment for different values of frequencies and tabulate the results. With this data, we can obtain the Bode plot of this system. As you can see, there are two asymptotes. For lower frequencies, there is a 20 dB drop per decade, which suggests a pole at s is equal to 0. And for higher frequencies, after approximately s is equal to 13, there is a 40 dB drop per decade. Hence, we can conclude that the poles are at s is equal to 0 and s is equal to 13. This is verified by the phase response, which tends to minus 90 degrees for lower frequencies and minus 180 degrees for higher frequencies. Now, we need to find the value of A. In order to do that, we can fit the model to one of the data that we have captured before, say the response for a 2 Hz sinusoidal waveform. By doing that, we can obtain the value of A and thus the complete transfer function model. With this model, we can design a controller to get accurate position control. It can be a PI controller, a PID controller, or any other type of controller. In this video, we will be designing a PI controller. You will be familiar with this block diagram of a unit feedback configuration. Expand the controller. As you can see, it's a PI controller. The only thing left for us to do is to find the values of Kp and Ki. As you can see, a transfer function of a PI controller would be of the form Kp plus Ki by S. By obtaining the characteristic polynomial of this system and by comparing it with the standard third order characteristic polynomial, we can obtain expressions for Kp and Ki since we know the values of A and alpha, and by taking beta and eta equal to 1, we get these values for Kp and Ki. Now that we have designed a controller, in order to assess the performance of the controller, we need to implement this on the system. So, I have set the values of Kp and Ki. Now, let us run this on the system. As you can see, I have given the step input of 360 degrees. So, we expect this motor to turn by 360 degrees and stop. As you saw, the controller caused it to overshoot and it corrected the error. There is a considerable overshoot and there is some settling time. In order to further improve the system characteristics, you can tune the PI parameters. This concludes the first video. Thank you for watching.